Let's now discuss how the pivots in a matrix affect whether or not the columns of that matrix are linearly independent vectors. You should think about the last example that we just talked about. Here I'm going to start with a matrix called A, and it has n columns, and I'm calling those columns v1, v2, up to vn. So those are column vectors. I'm interested in whether or not the set of those n column vectors is linearly independent or dependent. So our theorem is going to give us a condition that helps us know exactly when those vectors are linearly independent. So the set of my n vectors, v1 through vn, is linearly independent if and only if the following condition is met. I want to characterize that condition in terms of the pivots of the matrix A, the pivot positions. So if and only if A has a pivot in every, and what do you think it is, in every row or every column? I want you to think about the last example that you just looked at and answer for yourself. Must it have a pivot in every row, or must it have a pivot in every column in order to ensure that the set of vectors is linearly independent? And the answer is, you need to have a pivot in every column. The reason for this is that we want to make sure that when we reduce the matrix that we don't see a row with a column without a pivot and therefore a corresponding free variable in the solution set. That will guarantee that there are no non-trivial solutions to the homogeneous equation, and therefore, by definition, that our set of vectors is linearly independent. If that's not entirely clear, we're going to do an example right now and you'll see the theorem come to light. So here I'm going to take the matrix A. It's a 3 by 3 matrix. Its columns are 1, minus 2, and 0. The next column is 0, 2, 1, and 2, minus 6, 1. And what I'm interested in asking is whether or not the columns of this matrix A are linearly independent. And in fact, I claim that they are, so we're going to show that they are linearly independent. Let's just rephrase that in terms of the matrix equation. As before, the question we're asking is whether or not A times x equal to 0, the homogeneous matrix equation, has non-trivial solutions. I could always put 0 there. This equation is consistent. There are solutions to it. But the question is whether or not there is a non-zero vector that I could put there that would still be a solution. And if there was, there'd be infinitely many solutions, so we would expect the solution set to have a free variable in its description. Well, how do I solve any matrix equation? I augment it. In this case, I'm just going to put an extra column of zeros, and we row reduce. I'm going to row reduce by adding twice the first row into the second row, and that will give me a 0 in this position. Then I'm going to scale this row by 1, or by 1/2 rather. And then I'm going to use this 1 here in order to eliminate the 1 here, so I'm going to subtract that second row away. And notice I get a minus 2 here. In the previous example, it's very similar, but I had a 0 there. I did not get a pivot, but now in this example I don't need to do any further row reduction. I can see that there is a pivot, and pivot in every column of the matrix A itself. So let's summarize what we've observed. We're looking for the solution set to the matrix equation AX equal to 0, and we see that there's no free variable because every column has a pivot in there. As such, AX equal to 0 has only the trivial solution, and by definition, the columns of that matrix must be linearly independent of each other.